Hello, everybody. We talked about sets, what we call naive set theory, and a set was just a collection, and the things that belong to that collection were called elements. And so once we have this basic notions of set and element, we can do several stuff with that, and that's what we're doing now, operating with them, set operations. And the two very important ones, so if we have a set A and a set B, one thing we can make is the set A union B. This is called the union. And so what this means, as the word union probably already suggests, is we put everything together. So that is putting A and B together. And then the other thing we can do is A intersect B, that's called the intersection. And that is all the elements that are both in A and in B. So let me phrase this one more time in terms of elements, right? What does it mean for an element to belong to the union? An element A belongs to the union, so A belongs to the union. Sorry, let me write this a little bit more. A belongs to the union if A belongs to capital A or A belongs to capital B. Now, or, let's use our formal version of or. Let's write it this way. That is union. What is the intersection? An element little a belongs to capital A intersect capital B. That means that A lies in A and so if we use our formal notation for it, A lies in B. And you see that the notation is actually very similar, right? This symbol here is very much like this symbol, although it's just rounded now, and here the same thing. This is compared to that. There's of course a very obvious reason, is because they really almost mean the same thing, if you want. As far as elements is concerned, it is a union is an or and an intersection is an and. Now let's look at it, what it would happen on Venn diagrams. So let's do a particular example. Suppose A is a set of 0, 1, 3, 7, A and D, and B is the set 0, 2, 4, 7, A, B, and A, B, A, and B. Sorry, let me just do, I didn't want the C, okay. So let's calculate now what is each of this is. But perhaps before I do this, let's also look at what happens in the Venn diagram, right? So if we have a Venn diagram for A, and we have a Venn diagram for B, now normally we have some situation like that. So this would be the Venn diagram for A, this is the Venn diagram for B. What would be the union B? Well, let's see everything that is either in A or in B, so the whole blue spot. So this would be the union. What would be the intersection? The intersection would be the things that are common, so where the two Venn diagrams intersect. Okay, makes a lot of sense, right? So we could solve this problem by looking at Venn diagrams. So let's do it that way first. Let's make a Venn diagram for A and a Venn diagram for B. Perhaps my A should be a little bit bigger, right? Otherwise I'm going to run out of space. So make big A also pretty big. Yeah, sorry, that was not a good draw. I'll try again. Okay, so this is A, this is B. So, but here already comes a problem, right? So now we want to put in these elements of A, but we have to be careful where we're going to put them, because you notice that when you have two Venn diagrams, there are already basically 4 regions. Let's see what regions I'm talking about. Well, 3 you see, right? This is 1, 2, and 3. These are 3 regions here, but it's actually a 4th region, namely the outside of it. Because, for instance, if I want to put the number 5 somewhere, it's not in A, it's not in B, so the number 5 should go in the 4th region. Okay, let me get rid of these numbers here, because they're not really, it might almost look like I was putting elements in there. I was just numbering the regions. Now, let's go to the elements. So when we walk through the elements of A, remember it's an unordered collection. but we nonetheless have listed it in a certain order, right? That's the way English or any language works. It's this kind of linear, right? Otherwise, we don't know how to read things. So going from left to right, or if you want from right to left, 0. Now, when I put 0, as I said, there are 4 spots that it can go in. Where should I put it in? Well, I have to look at what 0 belongs to A, but it also belongs to B. So where should it go, you think? Right here, right? In what we call the intersection of both. 1 is in A, it's not in B, so 1 should go in there. 2 is in B, but not in A, so 2 should go in there. 3 is in A, is it in B? No, so it should be here. 4 is in A, but not in B, so it should be here. Let's take 5. Where does 5 go? Well, 5 is not in A, is not in B, so 5 really goes there. Okay? And same for 6. What about 7? 7 is in A and in B, so 7 goes in the intersection. What about 8 and 9 and 10 and 10? Of course, there are so many things that are not in these two sets. I cannot write everything down. There are too many, there are always infinite many elements, right? So where would I all put them, so to speak? So normally we don't fill up the outside part. But it's good to sometimes put at least some of things, make it clear that certain things are clearly not in what? In either A or B, so that would be not in the union, right? So 5 and 6 are elements that are not in the union. Okay, but we have not completely finished, so let me finish before we make our final conclusions. A is in both, so A should go there. B is in little b is in capital B. C is again not in either one, so just to keep track of where things are, I put it there. And then D is in A but not in there. So, and now I kind of have all the elements that were ever mentioned. Well, even 5, 6, and C were not even mentioned, but I just, for sake of completeness, I put them there. And we can now state everything. What's the union? A union B. What are the elements in the union? Well, everything that is into the blue shaded part, right? So that was, I forget now, was it light blue? This is our union, right? So everything that is in the blue shaded part, that is going to be in the union. That would be 1, 3, D, 0, A, 7, 2, 4, B. You say, Professor, but you're listing not in right order. What do you think about that comment? There is no right order. It's a set. You can list the elements in the set however you want, in whichever order you want. So I just read it off from the picture now. That's the union. And what is the intersection? Well, that's the red part, right? That's the part that they have in common, and that would be this part here. So the intersection A intersect B is 0, A, and 7. Okay, that's, I think, hopefully very clear how things work, right? You can have, you can do it to Venn diagrams, and you can do it just by enumeration. Now, there's a very important thing that we will shortly discuss. But before I do this, I want to talk about one important counting principle. We will talk about counting principles in discrete math 2 much more, but for now it's an important one, and it's called the inclusion-exclusion principle. Inclusion-exclusion. When I describe it, afterwards we'll come back to the name. Principle. And the question is about how many elements are in the union. So how many elements are in the union? So let's look at this particular instance here. How many elements are there in A? Well, 1, 2, 3, 4, 5, 6. How many elements are there in B? 1, 2, 3, 4, 5, 6 as well. So now you might be tempted to say, oh, the union therefore is 6 plus 6, right? It's either in A or in B, so 6 plus 6. What do you think about that? Is that correct? No, you see how many elements are in the union. 9 elements. So let's write that down. Here the union had 9 elements, just count them. So what was wrong by saying 6 and 6? Why is it not 6 plus 6? The 6 from A and the 6 from B. Because when you count the elements in A, the 6 elements in A, you say, okay, here, I'm going to count it. number 1, 2, 1, 2, 3, 4, 5, 6, and then B, 1, 2, 3, 4, 5, 6. So altogether, 6 plus 6 is 7. But what happens? Look at this count. When I'm counting this here, I also count it there. So the element that is in both of them is counted twice. And the same for the element A here, right? This element, when I count it here, was my fifth element here, and also the fifth element there, so I count it twice as part of the union. That's counting it too much. So you see exactly, and also the same for 7, exactly the elements in the union are counted twice. How many, in the intersection are counted twice. How many were there in the intersection? 3, exactly these 3 elements. So in the union, we had 9, we had the elements of A, there were 6 of them, and the elements of B, also 6 of them. But when we counted just each element of A and each element of B like that, we overcount. Some elements counted doubly. How many? Exactly the number of elements that are in the intersection are counted twice. So let's subtract that number once from it. And so this is the exclusion-inclusion principle. That tells you how to calculate the number of elements in the union. Sometimes people like to write this principle, people don't like negative signs, by putting this quantity also on the other side. Okay, this is an identity that you can play with sometimes. You can use it to find how many elements of a particular type are there, if you know the other 3. Okay, so for instance, let me do an example. So we know the following. If we know that A union B has 7 elements, we know that A has 5 elements, and we know that the intersection of A and B has 3 elements, then we can ask how many elements are there in B. I'm saying if you know how many there are in total, you also know how many there are of type A and how many there are of the same type, then you can figure out how many there are of the type B. Okay, and how do you do that? Well, okay, the formula 7 is A, 5, plus the number of elements of B, which I don't know, so I can't write it here, minus the number of intersection, 3. Right, there's a minus there, be careful, right? So bring this all to the other side, so that is, I do a plus 3, and do a minus 5. So here I have 10 minus 5, so 5 equals B. So we see that B has 5 elements. Oh, it happens to be the same as A, that's just a coincidence, I'm sorry. Now, you might think A and B always have the same elements, of course not, right? So another example of the inclusion principle, let's say, okay, we can use this in daily life. And so in a quiz, for instance, I will ask you a question like this. For instance, so in an elevator, there are 6 Hispanic students, and there are 7 math students, and Gonzalo is the only Hispanic math student. Okay. And let's assume that everybody in that elevator is either a math student or Hispanic student. In other words, there are no other students anymore. There's nobody else in this elevator. So the question is, how many people in the elevator? How many students, well, let's just say students. I mean, there might be a janitor in the elevator, so we're not going to count him. How many students in the elevator? This is all pre-COVID, by the way. Okay. That's weird, right? Now we have these things that look like so simple questions, and now we have to say, well, in the world before COVID, we could look at problems like this. Well, okay, so how would you solve this? Well, the way to solve this is to make a set, to make sets that represent the situation. Let's call H the set of Hispanics. So H is the Hispanic students. Okay. And M, let's call it the math students. I always like to call stats or remember propositions, so something that you kind of the letter that you assign to it is somehow related to what you're saying, makes it easy to work with, right? So okay, So what do we know? What is the question? How many students in the elevator? And we know there are other Hispanic or Met students. So we actually really asking what is the number of these guys. Okay, what do we know? Well, there are 7 Met students. So I know the number of Met students is 7. I also know there are 6 Hispanic students. So the number of Hispanic students, this is an M, okay, is 6. So is this enough information? You could say, oh, okay, that is 6 plus 7. But that's not enough, right? Because there is another way of formulating this inclusion exclusion principle is that there is an extra term, an error term, where the error is coming from double counting. So what is the error term here? So what we need is the number of Hispanic Med students. Now, Gonzalo is the only one, that means there is 1, right? So minus 1. In other words, if we put all the Hispanics there, we say there are 6 of them, there are 7 math students, and we say therefore 13 students, we are counting Gonzalo twice. We shouldn't do that. So it is 12. Okay, that's how you inclusion exclusion. And so if you want, what is it inclusion and exclusion means? Yeah, it's a little bit, perhaps you understand a little bit what we're doing, including everybody, but then we have to exclude the people that we counted twice, somehow like that. That's where this name comes from. Okay, there's one more set that we should look at and has a name, and let me do this in red to add to what we have here in the picture. When we look at this, we set there were 4 regions. The outside region, let's not for a moment bother too much about it. Therefore, for 3 regions, right? You have, let's look at these 3 regions again. This region we know, that's the intersection. But then there are these 2 regions that we should give a name to as well, right? So what are these? These are all the elements that are in A but not in B. And so that is what we call A minus B. So we read this as minus or not in. Of course, it's not really minus, right? Because minus is for numbers, but it's the set theoretic minus. So A minus B is also called the difference set. The difference between elements in A, the ones that are in A but not in B. Okay? So that's that region. And of course, there is a symmetric one. There's the B minus A, right? So let's give them colors. Let's call A minus B. Oh, no, not striping. I want the colors. A minus B, that would be this set. And then B minus A, of course, it's different, right? It's a different set. Let's make that in what color do I have not used yet? Yellow, perhaps. That is this set, B minus A. Okay? And so you see that the blue set, the union, consists basically of 3 separate parts. Namely, the A minus B, the intersection A intersect B, and the difference set B minus A. Okay. There's one more concept that I want, a name that is important because it's used so often. When we're dealing with intersections and so, we sometimes want to, it's very often happens that we have 2 collections that have nothing to do with each other. In other words, if A intersect B is empty, now how do we write an empty set? Remember, that was this 0 with a big line through it. So A intersect B is empty, then we say that A and B are disjoint. And that's an interesting situation that often happens. And it's also interesting when we go back to our inclusion-exclusion principle, because what happens in the inclusion-exclusion principle when the sets are disjoint? Let's look at this principle here. If these sets A and B are disjoint, that means that this is nothing. And what's this is empty set, and how many elements in an empty set? Exactly 0, right? In other words, then counting the elements in A and counting the elements in B and adding them up is the right thing to do, because the sets are disjoint. But if they're not disjoint, then you're double counting, and that's why this error term comes in. Okay, that's what we want to talk about. Now, there are many... yeah, right. So perhaps one more notation. So notation. We talked about the difference set here, right? the different sets between two sets A and B. But very often we're talking about U is the universe. There's this. So what does the universe mean? This is all these elements that are we currently interested in. Of course, it doesn't mean all the elements everywhere, because that would be infinitely many. But often our universe, or the universe where we work over, is, for instance, all the students at CityTech, or all the letters of the alphabet, or all the words in a dictionary, things like that. There's our universe. They often supposedly be finite. I remind you that discrete mathematics is mostly about finite stuff. So that's the universe. And so what we want to know, if we have so that's sometimes denoted like a square thing here, U, and it means everything inside that's the universe. And of course there's stuff outside in the actual universe. And then we have a set A here. And then what we really want to know is the elements in A, okay, that we can list, but we also sometimes want to talk about the elements that are exactly not in A. And that is, in other words, what we call the complement. The complement of A. So A being a subset of the universe, if it's the universe, all our sets that we are currently interested in should be subset of that. So the complement of A, what we mean there, that is, of course, the difference set. All the elements that are in U, but not in A. Remember, so the way that we read the difference is, okay, perhaps I should have said this also in a set notation. Let me do this in set notation. So an element A lies in here. What does that mean? That means that A lies in A and not A lies in B. Sorry, let me get rid of this word here. Let me write it again. So what does it mean for A to be, little a to be in the difference? It means that A lies in A and A does not lie in B. So this is sometimes written like that. That is the meaning of the difference set. And of course, here the meaning of this difference set, A lies, or let's call this guy now G, to give you a different name. G lies in a difference set means that G lies in B and G does not lie in A. Okay? And so what is the complement? That's all the elements that are in U, but everything is in U, that's the universe, that do not lie in A. So A lies in the complement of A means that A does not lie in A. That are all the elements that are not in all the elements in our universe, in the set of elements that we think about, that are not in A. Okay? That's the complement. Now, there are many set identities. So, set identities. When we have all these various operations, so for instance, an identity is that if you take the union with the empty set, let's think, what would that be, you think? If I'm adding nothing, well, I just have the original set. Okay, a bit harder perhaps to fathom is what happens if I take the intersection. I'll let you think about it. Well, if you want to think more, pause the video. Well, all the elements that are in A and are in the empty set, but there's nothing in the empty set, so this must be empty. Okay? So these are a couple examples of set identities. Another set identity, an obvious one, is some that I actually not even stressed, is that the order in which we take unions is unimportant, right? And another one is the distributive law. So the distributive law, so if you take the intersection with a union of two, so far we have been dealing with two subsets, but nothing prevents us to deal with 2, 3, 4 subsets, right? So if you take the intersection with the union, then it is the same as intersecting with the first guy, intersecting with the second guy, and what do you think goes in there? The union. Now, if you remember that there is an enormously strong connection between, between union and or, and between intersection and end. In other words, if you think of A, B, and C as predicates, and these guys become and or, then these are the familiar distributive laws of and or. And that's exactly what happens here. We are just a different way of representing these same propositional logical identities, propositional identities, become set identities simply because, as I said, a union is an OR when it comes to set membership, and an AND is an intersection when it comes to set elements. And therefore, and this is the whole point here, there's one important one, the Morgan laws. Let's think about that. What are the Morgan laws? Let me remind you the logical or the propositional of the Morgan law, not P or Q. If you negate a union, then you negate both of the propositions, but you put an AND in there. Now, what is negation? Where does negation come into? So far we had talked about union and intersection as OR and ANDs, but we haven't talked about negation yet. Well, we did. Look, here, right? This is logically equivalent with not A in A. So the complement is the same as the not. Oh, and I noticed a silly thing. I didn't give you the notation. I said notation and I didn't give it to you. Okay, so let me give you now finally this notation. What's the notation for the complement? We put a bar on top of it. So the not corresponds to a bar on top of string. So if we would do the Morgan law of the union, so the OR would correspond to union, the not would correspond to the complement. So if we take the complement of the union, then that's the same as taking the complement of the first guy, the complement of the second guy, and what do we do then? Intersect them. Now you might say that's weird to me. Okay, let's go to our example, our original example here. So we now have to make a universe here. So our universe is, let's say that this is our universe. In other words, it's the first 7 elements together with A, B, and C, and D, right there. So the universe consists of the numbers 1 to 7 together with the letters A, B, C, and D. Okay, that's my universe. Because now we can talk about complements. So let's now write down what our complements are. Sorry, I'm going to erase a little bit of stuff that we don't need. The union, let's have that. Okay, so let's talk about the complements here. Let me do this way. So what's the complement of A? That is everything that is not in A. And so which regions are we talking about? It's the yellow region together with the blank region, the ones that are outside the union. So this would be 2, 4, and B. That's the yellow region, the elements in B but not in A. And then 5, 6, and C, the elements that are in neither one. That's the complement of A. What's the complement of B? The complement of B, well, that is now everything that's in the green region, 1, 3, and D, together with, of course, the 3 outside elements. Okay. And now what was the claim here? That if I take the intersection of those 2 complements, I would get the intersection of the union. Let's start first. What's the intersection of the union here? Sorry, we are running it a little bit out of space. I can erase this, right? We have it on the picture. So what's the complement of the union? So the union was the blue thing, and the complement is everything that's not in the blue. So that would be 5, 6, and C. And now the claim was, if you take the complement of A and the complement of B and you intersect them, you look at the common elements, then you get this set. Does it convince you? Yes. What are the common elements? These 3 are the common elements, but these are not the common elements. So only these 3 are the common elements. It's exactly the one that I said. So you see on this picture, the Morgan law holds. But the Morgan law holds because it is the Morgan law for propositions applied to sets. And of course, this is the complement of a union. What's the complement of the intersection? What goes in the middle? The union, of course. Okay, good. So these are set identities. There are many more, and I'm leaving them. So there's a table in the book that you can look at. But what I now want to come to is, how do you prove these set identities? And you can use logic to prove them, but there's a much, much nicer thing to prove them. And that is, let me phrase it again. there is really seems to be not so much difference between propositional logic and set theory, where in the propositional case we have an and an or and a not, which corresponds into the set case as an intersection, a union, and a complement. So we should be able to go from one to the other. Now, what was one of the big tools that we had in our proposition case was truth tables. Well, why don't we use set tables? So what is a set table? Or membership table. Membership table. Well, it's like a truth table, but now instead of propositions we have sets, and we still use ones and zeros. And what is the meaning? The meaning, 1 will mean you belong to the set, and 0 means you don't belong to the set. Okay? So 1, 1, 0, 0, 1, 0, 1, 0. These are the, if you take an arbitrary element, then it has, it's one of these 4 possible scenarios that it can be in. It can be in both of them. Now, let's look at, on our picture again, we have colors, right? What represents the first line? Those are the elements that are in A and B. That represents the red guy, right? So perhaps I'll do this here. Okay, we can erase this here. We don't need this anymore. So let me make my truth table here. Then you see it much better. So we have an A and an B. We have 4 possibilities. As in the propositional case, right? The 4 different possibilities. I'm trying to be very systematic here. Some of you still were not very systematic, and then you get confused by the. Try to be very systematic here. Okay. So what at each of these regions? Let me now say. What does this mean? This is a case where elements are both in A and B. In other words, this is in this situation. The situation of the intersection. So this is the intersection part. What is the situation A but not B? That's the green part, right? That would be this situation. O. Right? This is these guys, right? These elements that are in A but not in B. What is the next one? Let's call it the next one. It's nice, right? They're doing coloring. It's yellow, right? And then finally, what is the last one? Well, that's the white case. I haven't colored the ones that are outside. Okay. Now, this is in this particular case, but the nice thing about these truth tables is they work for any sets A and B. Okay, so now what we want to show is that the complement of the union is the intersection of the complements. That is, in other words, we want to prove this set identity. Now, how do we prove a set identity? We're going to make the membership table. I'm going to very often say truth table because it's so similar. So let's call it the table. I'm going to make the table for this guy. I'm going to make the table for this guy. And what I want is to show that the 2 columns corresponding to these guys are the same. That means that these 2 sets are the same. So I repeat, 2 sets are the same if their membership tables are the same. Okay, so let's start doing that. First of all, what I need? I need A union B. A union B. What does it mean to be in union? It means that you're in one of them. So in each of these 3 cases, we are in the union, but in this case, we are not. And you see, this is exactly the same operation for the OR. This is as if we were doing OR here. Okay? Now we need to take the complement. What is the complement? Well, if you're in, you're out, and out, and you're in. That's how complements work. So that is just the not, right? That is exactly what we did, where we would apply in the propositional case, just not. In other words, we flip 0, 0, 0, 1. Okay. That takes care of this guy. Now we have to do the other guy. For that, we need a complement. As we said, that's just flipping 0, 0, 1, 1. We have to also put B. That is 0, 1, 0, 1. And now we have to take the intersection. What is intersection? Well, you can think of it just set-wise. It's the elements that are in both. So in other words, you have the 1 in both cases. And that's only in the last case. So that we would have a 1 here, but we would have zeros there, right? Or you can think of this as just an AND. And if you AND these 2 columns, that's exactly what you get. That's the end of this column. AND, okay? So here is intersection. I'm using the set theory notation. So what is this now? We have the table for this, and what we need, or the column for that. What we need to do now is verify that they're the same, and they are, right? This is the same as that. So okay, that's how you prove set identities. And of course, you can do many more complicated set identities. I wanna let's do. I'll make one up. I don't see one here. Well, I cannot make it up. I have to. Let's prove the set identity. Where is? I'm gonna take one from the exercises. Where are they? Oh, okay. Oh, I should say, yeah, okay. My notation, unfortunately, is always sometimes different, slightly different than the book notation, because it's the more, I'm a logician and I'm saying I know how these notations are usually used, and sometimes the book likes to use a bit different notations. I'm not saying they're wrong, but they're less frequently used. So instead of this notation, they write it really as a minus sign, and instead of this, of course, then also with a minus sign. Okay, so we understand that we can use either the slash way notation or the minus notation. I'll try to stick to the book notation. Okay, so let's prove. So show that the following statement. Where is this? B minus A. Oh, I said that we're going to do it with their notation, okay? B minus A union C minus A is B union C minus A. Let's prove this. Okay, show that this is an equality of sets. Now, in the book, there's a second way of doing that, is so-called by a proof, showing that an element, how do you prove that two sets are the same? By proving that they have the same elements. And how you do that? By taking an element in one set and prove that it's in the other. So you take an element in the left-hand side and prove that it's in the right-hand side. But that's, you have to do both ways. That this, if you take an element in the left-hand side and show this in the right-hand side, you have a set inclusion. But you also have to prove the other way, so you have to now take an element in the right-hand side and prove it in the left-hand side. I find that much more cumbersome than actually writing a membership table, so I am only focusing on membership tables. So let's do that with the membership table. First of all, how many rows are we going to deal with? Well, we have now 3 sets, so that corresponds to 8 possibilities, right? A, B, C, exactly as in the case of propositions. 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 0. Okay, now before I go on, let's just make the Venn diagram. Let's, on the Venn diagram, denote this, just a practice. I want to color on the Venn diagram this situation. So how does it would look like? Well, now we have 3 sets, and when we have 3 sets and 3 Venn diagrams, you have to make sure that you have all possibilities. So A, B, and C. How many regions are there? Well, if you count here, you see inside we have 1, 2, 3, 4, 5, 6, 7 regions. You say, wait, shouldn't there be 8? Yes, of course. Remember, there's an outside region. And the outside region would correspond to this one, right? So what does this one correspond to? 1, 1, 0. You mean you are in A, you are in B, but you're not in C. So you are in A, you are in B, so you are in the intersection of A and B, but you're not in C. If this would be also in C, so it's this part. Okay? And so any of these 8 rows corresponds to exactly one of the 8 regions. And you, if you like coloring, you can go and color this whole thing, or mark them with numbers or something like that. That's just, I just wanted to show you that we are dealing here with what is in reality, what these truth tables or these membership tables tell you in a concrete setting of a Venn diagram. Okay, but going back to our proof, now we need to do B minus A. Okay, we need the truth table of B minus A. Now we have to think about that. What does that mean? We have to look at elements that are in B but not in A. That means we want a 1 in B column but a 0 in the A column. Let's look for situations where this happens. This is the two situations that I see where this happens is this one and this one, right? These are the only two cases where we have a 1 in the B and a 0 in the A. So these are the only two cases when we have an element in that set. So this is 1 and this is 1, and everything else is a 0. Right? So these are zeros because this would be an element that's both in A and B, that's not in the difference, and so on. This is an element that is in A and not in B, which is A minus B, not B minus A, and so on. Okay. You might ask, what does this correspond to in the logical setup? It's you can think about a little bit. It is a kind of an implication, but let's not think about that because it's a little bit subtle. You have to. It's not direct. It's not B implies A, for instance. Okay, so in fact, it's the negation of that. If you want to know. Okay, so what about a C minus A? Well, the same thing, but now. So by the way, I hope you don't get confused by this yellow thing. This yellow thing has nothing to do with what I'm trying to do here. That was just for the illustration down there. C minus A. So now we're looking for 1s in the C column, but 0s in the A column. Do I see this? Yes, I see one here and I see one here. And that's the only two cases, so all the rest is 0. Remember, it's always for each case, for each of these different things, you're trying to say, when do I have a 1, when do I have a 0, and then if you establish all the 1s, then you know that all the rest is 0. That's easier to do. Okay, so now we need the union. So B minus A union C minus A. Zoop. How do you do union? Well, that means you have to be in either one of them. It's an OR. This really is an OR. The first 4 are zeros, so that both have zeros, so that cannot be. But here we would have a 1. This would be a 1 because it's at least in one of them. This would be a 1, but this would be a 0 again. So these are all zeros. Okay. Good. Now B union C. This established the left-hand side. Okay. So now B union C. I need that first. B union C. That's a union. So I have to be either 1. So there's a 1 here, a 1 there, a 1 there. That would be a 0 because there. Remember, we are now looking here at these two guys, right? B's and C. Okay, and also here that would be a 0, and all the rest would be 1s. Okay, double check that is correct. And then finally, B union C minus A. What does that mean? That means, remember, we want a 1 in this column, but a 0 in the other one in this column. So we want zeros in this column, so we should only look in the bottom here, and then we want 1s. We see that these 3 are 1s here. So each of these cases we get a 1. We get a 1, a 1, and a 1. Okay, and so where are we now? No, wait, B unit C, yes. In B unit C, but not in A. There's a 3, and so the zeros otherwise. Okay. And so now is the question, are we, this takes care of this, so we have this and that. Are they the same? So is this the same as this? And luckily for us, it is. So that's how you prove ideal membership. Okay. One more last thing, and that is also something handy because after all, discrete math is very, very much connected to programming, and many of you are actually taking it because you're in a computer science program or related program. And so another thing is often we want to represent sets in a computer, digitally in a program. We wanna and how do we do this? So a computer representation. So take for instance, we have the set A is the set of all vowels, say A, E, I, O, U, and okay, I guess the textbook doesn't want to put Y in as a vowel. It is a vowel. It's sometimes vowel, sometimes it's not. So I'm gonna put it in there just to be different. I don't want to be always compliant. Okay, so I'm saying these are my 6. That's my set A. And I want to represent now subsets of this set. Okay, so this is basically, let me call this my universe, perhaps. It's better to call this my universe. And then I'm talking about subsets of vowels. Okay? So, how am I going to represent these? Well, a set is an unordered collection of objects, of elements, but if I want to represent it, I have to order them. So we choose an ordering, and let's choose the ordering here, the alphabetic ordering. Here we take the alphabetic ordering, but you could take other orderings. You could just arbitrarily order them, just list them in one way or the other. You say, I like to list everything as O, U, Y, E, I, E. Why not? But once you fix one, and this is something you need to know in advance when you're using these codes for these for the subsets, you need to know what the ordering was that you chose in the beginning. So we fix this ordering. So choose, let me even put it more firmly, fix, Ella, what happened here? Fix ordering. And now I can, so let's say I want to represent this set. Okay, how do we represent this set? Well, when the element is in, so A, so the code for A, so how the code would look like? It's a binary code. The binary code for A, well, there will be a 1 if the first element is in there, and a 0, the first digit will be a 1 if the first element is in there, and the first digit will be a 0 if the first element is not in there. So A is in there, so we get a 1. What about E? So remember, now we are going through this list in this particular fixed order. What about E? E is not in my set, so that becomes a 0. I, not in the set, that becomes a 0. O, it is in the set, it becomes a 1. U is in the set, becomes a 1, and Y is not, so it becomes a 0. So the binary code for this subset is now this. Okay? So, what this means is that we can now, every subset is represented by a binary code. Now, and this is not like you could say, okay, so big deal, but it is actually nice. Like, let's look at another subset. Let's say the subset A, this subset. What's the binary code here? So the binary code for B, 1 is in there, E is in there, I is not in there, O is not in there, U is in there, and Y is not in there. Okay? So now let's suppose I want the binary code for, what happened here? Binary, okay. Binary code for A union B. So the code for A union, I'm just going to write code. Now I could calculate what A union B is, but what I also can do, here, let me put this here on top of it, I can just carry out a binary addition which corresponds to OR, right? The binary condition, a union corresponds to OR, and in the binary world, that means if you have two, whatever one of your digits is a 1, then it becomes a 1, and only when you have a 0 it is a 0. So 1, 1, 1, 0. We ORing here. It's like when you think of this as truth tables, and this is okay. This is supposed to be the columns of my truth table, but I've written down as rows. But other than that, I'm ORing them. So I'm saying my code is 1, 1, 0, 1, 1, 0, without actually really calculating what the union is. That's nice, right? And now I can double check, right? What does this represent? Now, when I have a code, I can also look at what are the elements that a code represents. Well, the first one tells me that A is in there. The second one tells me that E is in there. The third, 0, means that I is not in there, so I'm not going to write it. Then the fourth element, O, is in there, U is in there, and the last element is not in there. So this code represents this subset, and that is exactly the union. And of course, what's then the intersection? The code for the intersection. Now we have to end, so we do 1, 0, 0, 1, 1, 0, end 1, 1, 0, 0, 1, 0. That's I'm going to do this here. So I'm now going to do an end here. Sorry. And the end means You have to have a 1 in both, otherwise your bits turn 0. Okay, so this is 1, 0, 0, 0, 1, 0, and this represents, what is the set that it represents? Well, the A is in there, so let's see. A, E, O, I'm forgetting a letter. A, E, I, O, U. So U is in there, and that's it. And is that intersection? Exactly. So you see that these codes represent binary strings, and then the set operations on these codes correspond to binary operations on these binary strings, the and and or on these binary strings. That's what it makes it useful. And so now I could ask you, so what is the complement? What's the complement of A? The code for the complement. What does that do? Well, it's flipping the bits, right? So the complement of this will be 0, 1, 1, 0, 0, 1. Okay? And so just what's the code for spontaneously? What I mean here is give me all the vowels that occur in this word spontaneously. So let's start. Okay, what's the code for the set of all letters, all the vowels in the word spontaneously? Okay, so what about A? Yes, A is in there, so I get a 1. What about E? Oh yeah, E is in there, so I get a 1. What about I? Oh, I is not there, so I get a 0. What about O? Okay, O is in there. Oh wait, O is in there twice, so I should put a 2 there? You really? Remember, in a set where you list an element once, twice, 5 times, or many times you want, it only counts once. Sets are, an element is in a set or it's not in it. There's no 5 times in a set. The same element is only once there. So, of course, not a 2. Okay, I hope that was clear. There has to be a 1 here. So let me here put on top let me remember the order here. So we were now talking about, oh, what about U? Yeah, U is in there, so I get a 1. And then Y. See, this is a vowel, right? This is not a consonant here. So we get a 1 here. Okay. All right, enough playing with that. I'm going to give you homeworks, problems, and then perhaps also a quiz. And the quiz, the 2 things that I want you to really know is dealing with membership tables and proving set identities membership tables, and also using the inclusion-exclusion principle. Those are the really 2 main things that we learned, but of course all the other things were there to set this up. Okay, see you guys in the next lecture, video, home solutions, whatever it is that you watch next. Bye-bye.